Hey everybody, welcome to the first video in this ODE's lecture series. Let's go ahead and get started with a little bit of an introduction to what we're going to be doing in this lecture series. So in the intro video, I tell you that this is going to be my presentation of a university level course, your first course in ordinary differential equations. So in order to get moving on that, I kind of have to tell you what a differential equation is. So first, why would we even care to study these guys? Well, it is very often the case that we are studying some sort of physical phenomenon, and we would like to be able to predict its long-term behavior, or to be able to tell you what is going to eventually happen in this system, what is a noteworthy feature that you should look out for. Is there anything strange about this that may not be evident just from creating the model? Well, yeah, a differential equation would actually describe a lot of these situations very, very well. And they actually do wind up simplifying some work that would be very tedious otherwise. And what I do mean there is, instead of going out into the field and procuring your data empirically and saying, here's what a trend looks like, no, this is something for statistics to take care of. No, what we would like to do here is preemptively create a model so that we don't have to go out into the field, or that we don't have to go out into the field so often. Yes, getting empirical data is how we even have an inkling of what our model should look like in the first place. But once we have that tiny bit of information, we can save ourselves a lot of work in the long run. So these differential equations do show up in just about every branch of the physical sciences, and actually in some cases it shows up in the humanities. So you could even talk about interesting applications in political science or in psychology, and it's very, very interesting that these would show up in such a way, in such a liberal arts fashion, or in something that seems not very numerical to begin with. But my favorite reason for studying these differential equations is because they are just plain awesome. Like they are really, really fascinating, and have a very integrated theory, integrated mathematical theory with a bunch of other subjects, other fields, other branches of math. And I really enjoy taking a look at these and showing how they work and explaining how they work to other people. So, first and foremost, we will tell you that a differential equation is just an equation that contains derivatives in it. Okay? That's all it is. It sounds like something really fancy, but honestly, there's not a whole lot more to it than just saying that it's an equation that relates a function to its derivatives. And I'll give you this gigantic list, right? There's a whole list of different applications that I'll start off with to tell you where these show up or how they might show up. And first, if you checked out the prerequisites for this class, you needed some integral calculus. And that class is actually the first place where you encounter differential equations, right? So these guys came in the form dy dx is equal to f of x, and our job was just to solve for y, right? We needed to figure out how to create antiderivatives of functions. And that was a really, really pivotal class that gave us a good starting point to start talking about how rates of change influence functions, and how functions are what functions really look like and how they behave. So that was what we did in Calc 2. You may have seen this either in Calc 2 or possibly as early as Calc 1, where you talk about maybe population growth models, or maybe finance, or you talk about exponential decay, like half-life models. That would be this guy down here, this dB dt equals r times b, right? This is just saying that the number of the number of members of some population grows proportional to how many members are in that population. That would be a Malthusian growth model, right? That's yet again a differential equation dictating how something behaves, or telling us how something should behave. Not only do we get differential equations, but we get kind of a fun discrete cousin of these guys. If you don't want to use a continuous time model for your simulation, then you would defer to something that is in discrete time intervals. So where you would be checking back every month or two, or a good example of this might be the U.S. Census. We take this every 10 years, right? This would be discrete time intervals. So this would be a very closely related object, but not quite a differential equation. This would be something called a difference equation. And the one I have listed here is a very popular difference equation. This is called the logistic equation. It's a very, very popular example because it creates, it's a nonlinear equation, and it actually has a lot of very interesting behavior as you change that R parameter. You might go check out the dynamical systems playlist for more on that model. Differential equations can also be model multiple objects at the same time. So a very popular predator-prey model was proposed by Lotka and Volterra. That would be what would it be? This would be father-in-law and son-in-law relation, if I remember correctly. Let's see. The idea is that you could model how different populations influence one another. So in this top row, you would be thinking about how the number of rabbits changes at a given moment in time. It has a Malthusian growth parameter, but it also has a mixing predation factor. And in the bottom row, you'd have foxes and how they change over time, or how they grow or decay over time. And there's a competition term in that -CF, and there's also a growth term based on whether or not these foxes can find and predate rabbits. So we will talk about that model in particular much, much later, but we can set up systems of differential equations. And not only can we worry about first derivatives, we can also create models based on second derivatives. And these show up very, very frequently in physical models because life does not happen without second order, or motion does not really happen without acceleration. Or interesting physics doesn't happen without acceleration. So we will often see physics as as something that produces a lot of differential equations. And this one actually comes out of Newton's second law, and so does the one beneath it. But this is the mass spring, the damped mass spring system, and it's actually forced when this f function is non-zero. But if the f function is 0, we call this the model for the simple harmonic oscillator. Right, very, very popular model. And b would actually have to be 0 as well. Yes, simple harmonic motion. It's periodic motion, sinusoids. And we will show how we know that, or how we can get that. Number 6 here is talking about another Newton's second law application. This would be the rigid-armed pendulum. And this is just called the pendulum equation. It is yet another differential equation, another equation that uses second derivatives. And not only can we talk about ordinary derivatives, these single variable function derivatives, we can also talk about multivariable function derivatives. And number 7 here is something that shows up in a lot of different physical applications, most notably in electrostatic potential and in fluid flow, but it also shows up in complex function analysis. And this is called Laplace's equation. Solutions would be called harmonic functions. Number 8, probably the final example I'll take for right now. This is the heat equation, right? It is another partial differential equation, and these show up all the time in time evolving systems where you have multiple spatial parameters to deal with as well. But this list could go on forever. There are a great many compendia, right? A whole bunch of lists everywhere, telling you, here are the equations that we think are interesting or are the most notable. And it's just a matter of opinion, right? I'm just giving you a whole bunch of equations because these guys will be used in the next section when we talk about how to classify differential equations. So this is where I want to cut off this video, because I would like to tell you how these differential